Data science is the study of data, right? So whether you're doing data science in terms of data analysis, the foundation part, or you're doing to the part of AI development, working with machine learning models, okay, the idea is basically the same. We're trying to make meaning out of data and see how far we can work with data to help our lives become what easier. Okay, so our objective is basically what to understand what data science is, explore the life cycle of a data science project, okay, identify different roles in data science ecosystem. Okay, so basically, data science is the combination of what multiple disciplines that uses statistics, data analysis, and machine learning to analyze and to extract knowledge and insights from what data. Okay, so that is basically a simple machine learning or data science introduction. Okay, you're trying to multiple disciplines, okay, to use what statistics, data science, and machine learning algorithms to analyze data and extract what knowledge and insight from it. All right, so now um, this is a much more in-depth explanation as to what we have above. Okay, the main goal is to use the data you gathered. Okay, the main goal is to use the data you gathered to what to make decisions. That is the main goal. To use this data you gathered to what make decisions. Now, data can be structured and unstructured. Okay, which means the format in which data was received can either be a structured format or a an unstructured format. Then data analysis or rather data science is about finding patterns in data. Okay, so at the end of the day, we need to find patterns. When we can understand these patterns, then we can begin to make some predictions based on what the patterns we've understood. But that is all data science is all about. Data, find patterns, analyze, make predictions, and what use the predictions for what inform decisions or decision making processes. Okay? By better decision making, what do we mean? For instance, you're working in a company and you are about to decide if we would go with feature A or feature B. For instance, the company you're working with produces a let's say a particular kind of eyeglass, right? Now you're deciding the color shade for the eyeglass. Should it be black or brown? So why are we choosing black? Why are we choosing brown? Okay, so these are the questions you need to answer. And if you have enough data backing it, then you can make the right decision, not just a random one. Okay, so that is what this is all about. Now, in a company that has big machines, keeping record of each time you make maintenance or you perform maintenance can help you predict when next your maintenance should do what occur. Okay, so that is predictive what analysis, where you determine okay what has happened, what will happen, and then proceed from there. Okay, so the key concept, like I said, is just with what discovering what patterns between or within what our data. Okay, discovering patterns within our data. And by now, we've seen how we work with data, how we clean data, how we try to understand the data, the univariant analysis, the bivariant analysis, and the multivariant analysis. We've done all of that correlations and the rest of them. So all those things we did was just preparation for where we are going to next, which is the machine learning aspect. Okay. Then we will skip this down to the point of what life cycle for data analysis or data science projects. What is the life cycle for data science projects? We always begin by what? Defining the problem. I'll always hinge on this because if you don't know what the problem is all about, whatever you're doing is waste of time. Okay? Even if you can collect data, what are you collecting data for? Right? So always know what the problem you are trying to solve is all about. And if you are to build or analyze something that doesn't solve a specific problem in the company, you are wasting resources, basically. All right? So that is one. So a company wants to reduce customer churn, which is the rate at which customers cease doing business with the company. So if the goal is to reduce customers from churning or leaving the company, then you have to what? Find data that aligns with the goal, basically. Since the problem is that customers are leaving, so the question is, why are they leaving? How do we now stop them from leaving? When you know why they are leaving, you can now stop them from what? Leaving. Okay? So that is basically a problem statement or business logic. Then after you've gotten the business logic, the next thing is to collect the data, which can be in any format. All right? We've seen can be in SQL format, can be in Excel formats, basically any format, CSV formats, form formats, even APIs from other applications. Okay. Once you've collected the data to one single source, then we begin the pre-processing. We saw how to handle null values, missing values, duplicate values, outliers, okay, and inconsistent what? Data. Alright, so outliers are basically data that are beyond what you're expecting, okay, beyond the range you're expecting. For instance, if you're expecting the value to be between 200, all right, to 3,000, and you're seeing a value less than 200, way less than 200, let's say 20, for instance, or you're seeing a value that is way more than this, let's say 5,000, right? Now, this is basically samples of what? Outliers. They are values that are beyond the expected what? Range. Okay? So, the outliers, they don't fall within the interquartile range of the data set. Then duplicate values are what you know about already. Duplicate values are simply records that are multiple times. Then missing values and values that don't even exist at all. Okay? Then inconsistencies are usually all of them. Okay? Conversion of data type from one to another, okay, and normalization of features. We saw all these things. Okay? So we use pandas to do it, we use NumPy to do it, we use OpenRefine to do it. Okay? Then we saw exploratory data analysis. So after you've done cleaning, we saw how to explore, to find out patterns and visualize them, okay, using Seaborn, Matplotlib. You can also use Power BI, Tableau, Excel, okay, for visualization as well. Then we did feature engineering, where I talked about we created what? New features for the already existing feature. For instance, if you have the dates and you want to get the month or the year from it, or the day from it, you can actually get the day which has the most cell or the month which has the most cell just from having what? The date only. Okay, we also saw all these things. Then we moved over to, okay, we haven't done this part, model building, right? Model building. This is now where we talk about building of your model, where we're actually going to start within this class. For model building, we have many tools for it. One is scikit-learn, which is what we're going to look at. We have TensorFlow, we have Keras, we have PyTorch, we have Fast AI, okay, and we have other ones. We have transformers and the rest of them. But for the sake of this class, we'll start with scikit-learn and then probably progress to TensorFlow and Keras. Okay. Then model building is basically building of or training what we call AI. Is basically the model building itself. Okay. So we have types of models that we can build: classification models, regression models, clustering models. We're going to see the differences between them. Okay. Then after we've built our model, the next thing we're going to do is to check if this model is performing optimally. Is it doing what is expected to do? Okay. How accurate is the model? Okay. That is the next thing we're going to look at. After we've seen how accurate the model is, the next and the last step, okay, is to deploy your model. The whole point is to build and deploy, not just to solve the model in your system. Okay. The next point is to build and deploy. After you've built and deployed, okay, now it's time for you to sit back and watch people use it and monitor and maintain the model, basically. So that is exactly what your life would look like as a data science or a data science person. Whether you're in the analysis field you stop at approximately here, feature engineering at most. You won't get to model building, okay? Feature engineering at most for data science, for data analysis people. Then for those that are moving up to AI and model building, you get to deployment and maintenance, basically. Okay, so that is that. All right, this is the basic reintroduction. So we start with our first machine learning program or course. Okay, I can drop this one for us, but okay, we start with our first machine learning course, which is supervised machine learning. Okay, so this is where we'll start. When it comes to machine learning, okay, there are two types of machine learning. One is supervised, the other one is what? Unsupervised, right? So even though we have a third type that is mostly like semi-supervised, okay, or what is called reinforcement learning, okay? Reinforcement learning, to be more precise, not semi, reinforcement learning. Okay, so but our focus for today is on what? Supervised machine learning. Okay, so the supervised machine learning is basically the machine is trained to learn from labeled data. Okay, so machine is trained to learn from what? Labeled data. And then we apply the knowledge to predict what? The level of a new data set. Basically, what it's all about is we bring our data after we've done the cleaning and the whole preparation process to where we start model building. Okay, now we now say, okay, we divide our data into two. One is the label of the data, the other one is what we use to predict the label. Okay, so known as the independent variable, while the other one is dependent variable, or I'll call it features and then targets, right? So the target is majorly what? Our labels, while the features are what we use to predict what? The labels or the targets. Okay, so that is that. Then types of supervised learning, we have regression. Okay, regression deals with when we are trying to predict continuous values. Okay, regression deals with the prediction of what? Continuous value. For instance, when I'm predicting the house price, okay, house price, stock price, or temperature of a place or whatever, okay, now I'm dealing with the prediction of a number, an actual number, a continuous number, okay. Then we have classification, which deals with categorical values. Here I'm not predicting for a number, but rather I'm predicting for a class or a category. For instance, gender, okay, to predict if this is a male or a female, something like that, or to predict if this is a luxurious apartment or not, to predict if this email is spam or ham, depending on the case study. Okay, so at this place I'm predicting a category, not necessarily a value. Okay, so regression problem deals with prediction of values, while classification problem deals with what? Putting your data or predicting the classes of your given data. Okay, predicting the classes of your given data. All right, so those are the two major types of what? Supervised machine learning. One, regression, the other one what? Classification. Okay, so that is that. Then we move gradually to see regression in details. Okay, we'll see regression and see the what? Algorithms that are possible before we start using some of them. We won't go into using all these algorithms. Okay, we just use one or two of them, then we proceed to the next one. Okay, so regression models make the use of features to understand the relationship among the continuous features, okay, and the output variable. Now, what is just trying to tell us is we are trying to make sense of the relationship between a continuous feature or our features and our output variables, as the case may be. Okay, then that is they use the pattern that they learn to determine the value of the new data point. This is a technique that predicts the value of a dependent variable y based on the independent variable x. Okay, so we will see me split our data into x and y consistently. I don't know if you watch that video I sent you, we are seeing the guy, you see the guy split these things into two as well. Okay, that's for those of us that are in earlier classes. Okay, but the x is majorly what our independent variables. These are the things we are using to predict, known as the features. While the y is what we are trying to predict, known as the dependent variable or the output variable. So common regression algorithms are linear regression. Okay, so we have polynomial regression, we have the decision tree regression, we have random forest regression, we have support vector regression. Okay, so we're going to look more into linear regression. We're going to start with linear regression first, and then we gradually move into the rest. Okay, all these things are like mathematical functions, so just know that they are mathematical functions or algorithms, as the case may be, and they behave slightly different from each other. Okay, the linear regression then seeks to find a linear relationship between the y and the x of it. Okay, why the polynomial, like the name suggests, okay, decision tree basically seeks to find if there is a connection in terms of branches, right? For instance, at this point, if I'm at point A going to point B, what is the relation? Not necessarily like a mathematical formula, but in terms of decision. If I go here, think of it, it's trying to minimize the maximum, or how should I put it, minimize the number of trees it needs to use to get to the optimum decision. Okay, that is for decision trees. Okay, then we have random forest. Random forest is like multiple decision trees together. Okay, that is random forest. Then we have the support vector machines, which are more used to, I don't know if you've heard the word hyperplane before, because most of them I can't actually explain them in simpler English. Okay, there's no other simpler English I can use, but to use the same terminology that I was used. Okay, but basically, these algorithms help us achieve our goal in regression. Okay, and remember, regression is when you're trying to predict a continuous value. Okay, trying to predict a continuous value. All right. So let's look at the linear regression, which is, well, obviously one of the simplest and one of the most impactful. Okay, it's simple to use and at the same time very, very robust. Okay, then linear regression is a type of supervised machine learning algorithm that learns from labeled data sets and maps the data points with most optimum linear function, which can be used to predict or for the prediction of a new data set. Okay, it assumes a linear relationship between the input and the outputs. Okay, so for example, we want to predict a student's exam score based on how many hours they studied. Okay, so we observe the student that studied more hours, their score should be should go up, and the student that didn't study more hours, the score should be go down. Okay, so in the example, the predicting of exam scores based on study hour, okay, goes to denote that we have one, our input or independent variable x, the study hours. Okay, so when it comes to the data set, we majorly, like I said, we have two. All right, in our case, we have hours the students study or study hours, right? However, to it. Then exam score, which most likely spell exam score correctly. To do like this. And then let's assume that we have just these two. Now this is our X, this is our Y. Why? Because I want to use this part, the study hours, to predict the exam score, basically. So whatever I'm predicting is the Y, the output. And whatever I'm using to predict it is basically what? The X. Okay? So that is that. And S can be more than 1. It can be 2, 3, 4, 5, 6, as the case may be. Alright? So, but in most cases, our Y is mostly one column, basically. Alright? Now, types of linear relation. We have positive linear relation, negative linear relation, and no linear relation. Okay? So, the positive linear relation simply means that an increase in one will lead to a decrease in the other one, and rather an increase in one will lead to an increase in the other, while the negative connotes that an increase in one will lead to a decrease in the other. Then no relation or no linear relation simply means that there is no accurate representation of the model linearly. So it doesn't really matter. I can't tell if an increase will lead to an increase or an increase will lead to a decrease. Okay? So that is that with the whole theory introduction. We are moving into the code straight ahead. So we start writing some things to prepare ourselves. I think by default you should have scikit-learn installed in your system. So try doing this. If it doesn't work, then you can write the command on top. Okay? So we start by importing. We have this data set now, right? Data.cv, CSV, right? Okay. So we'll start by doing a basic import for that, and then we'll proceed. This one?
Yes.
This is scikit-learn.module selection, import train test split, scikit-learn.linear model, import linear regression. Scikit-learn that's sklearn, right?
Yes.
Mm-hmm. Dot matrix import mean square error. Model and selection.
Oh. What was the
Linear model.
what I wrote yes.
You have error now.
No, I'm trying to.
Okay. Remember that you also write your own CSV like this. So I'm writing like this because of the way I saved it. Okay, so you can always put just data.csv and save it in the same location. Okay, so then for those of us that have gone beyond this level, you can do the info that we did, right? Then check it for null values like we normally do as well. Okay. So the flow is basically the same, very simple. We start from loading our data, trying to understand a few things about our data, checking for missing values. All right. Then we progress to removing them if any. So we saw we have 5 missing values from our calories column. Okay. And we went ahead to drop them. Then we checked again and we discovered that we don't have any anymore. Okay. Since we all have numerical values, we can easily do a correlation to get everything we needed. Okay. So ultimately, we are still following our data analysis approach, where we went from trying to understand our data sets down to dropping null values or removing null values or handling null values. Okay. If these null values were many, I could have chosen to fill it with 0 or gone with the median or the mean, depending which one. But I can do a forward fill. Okay, so it depends on what we're trying to achieve. Again, we went from there to running.info to see what we needed to see, checking our null values, removing the null values, checking it back. So it's just a repetitive process. Then, remember what correlation is doing now? Correlation is for what? Checking the relationship between multiple columns. Okay? A column against another column. Alright? And I said that the one that has 1 simply means that we have what? Perfect correlation. Any other thing beyond 1 is between 0 and -1 and 1. 0 in between. Okay? So if I'm seeing negative values, it simply means we have what? A negative correlation. Okay? So that is that. And values that are closer to 1 denote strong correlation. Right? Like I'm seeing 0.9. Right? I'm seeing 0.9 for duration and what? Calories. Meaning that the longer you exercise, the more calories you burn. Is it not? That's the meaning of the high correlation. Why the lower you exercise, the lower the calories you burn. So it can make sense with that from your head. Then the other one was high again. The max pulse and pulse itself had 70. Okay, so it makes sense for the pulse to have correlations that is high. Okay, so that is the correlation we have seen. So looking at this data critically, you already know that from what I'm expecting, there is a connection between what? Calories, bonds, and duration of exercise. And the max pulse and the pulse themselves are also what? Correlated highly. That's how this is what you have in your mind while proceeding to do what? Do your analysis or build your model for prediction. Okay? So now, after you've done this, you don't have much to do. We're not going to do any much invariant analysis to try and find out all those stuff. Okay? Our goal now is to do what? Is to train and build our model. We've seen how to do data pre-processing, data cleaning. We've seen how to do EDA, which is our exploratory analysis. Now we're going to look at how to build models, at least a very basic linear regression model. Okay? Now the first thing is to identify our target variables or dependent variables, okay, which is basically what? Our Y class, okay, our Y variables. Now for us to identify that, we are trying to, in our case, we are trying to predict the calories needed, okay, or trying to predict the calories that you will burn from your body, basically, after exercise. That is what we're trying to predict, calories. Okay, so based on what we see here, which field do you think is the most important for calories? We're trying to predict calories, like how much energy you burn for fat you burn, whatever you put together. Okay. Now we have chosen Y. The reason why we chose Y, okay, can vary. But for this class, you don't have any particular reason, just choose Y. because that makes the most sense for us. Okay? But at least for an exercise, we want to predict how much weight the person will lose. Okay? So it makes more sense to predict weight loss or calorie response than to predict the beat of the heart. Alright? So people can control their heartbeats. Now, based on what we selected as our Y, okay? Based on what we selected as our Y, which variables will make most sense to include in our X? That is another question you should have at the back of your mind. Okay? You don't just select these things randomly. Most times to select a particular a particular target variable, you need to do it based on the question that was asked or the problem you're trying to solve. In our own case, we don't really have any question we're answering. We're just following our script. Okay? So, moving ahead, again, we've taken our Y, then we are left with our what? Our X. Notice that I also took X and Y at the same time. So whenever you pick the Y, you remove it from what? The X. Okay, you can't want to predict, or you don't want to predict the Y and still have the Y inside of your X. Okay? You don't want to predict the price of a house or the price of something or the weight of somebody and you still have the person's weight and what you're using to predict. Okay, so whenever you're doing that, you always drop the column that you've selected for your what? For your Y. Okay? Once you've dropped it, the balance becomes your what? X. If you want all of them there, or the most important one becomes your X. If you want only few there. Okay? Now we just have to print our shape to see the columns and rows we have. Now what we did here was to separate our data into what? Independent and dependent, or feature and target. Okay? The next thing is to separate our data into what? Training and testing. Okay? So we are doing two major separations. The first separation is to break it down into what? Two groups. The first group is to say, I'm predicting for this, and this is what I'm using to predict it. The second one is to choose the data you're going to use to train and the data you're going to use to do what? Test. These are the two important splits in our selection you're going to be doing. We've done the first one, which is selection of our target variables and our independent variables. The next one is to select or break our data into parts such that we can use it to do what? Train and test our what? Our models. Okay? So that is that. Proceeding further, okay. Now, for us to split our data sets, we have a particular function that we normally use, okay, and it's called the train test split function. The train test split function. It allows us basically to take our X, take our Y, and then break it into what? A certain percentage. Okay? By default, we normally use 70% of our data and above for what? Training. Alright? Then 30% and below for what? Testing. Okay? So, what do we normally pass inside of our train test split function? We pass in the X, which is our independent variable. We pass in our Y, which is our dependent variable. Then we are saying test size, which is the size of what you want to keep for testing. Okay? We are saying test size. Now, you're putting a decimal number, a floating point, which signifies 0.3, which is the equivalent of what? 30%. Okay, so it's basically 1. 1 meaning 100%. Okay, so 0.2 is 20 what percent. 0.25 is what 25%. Okay, so by putting what 0.3 and signifying that I want to use what 30% for testing. All right, then I'm setting a random state. This random state tends to shuffle our data set. Okay, now by default, if I didn't put this, each time I run this, it keeps giving me different variations of what our data. Okay, but by setting this, it will keep giving me a constant value every time based on what this random state. Okay, so if I remove this random state and leave it blank, it will by default start giving me random behaviors, random values on its own. Okay, so then again, if I, like I said, if I run it over and over again, it keeps changing. I can't really tell which set of data perform the best or performs well the most. Okay, because each time I run it, it gives me a new different shade of data. Okay, think of it like this: it's going to randomly select or split the data based on what you have. Okay, but setting this means you're giving it a random state already. At what level should it remain permanently? By setting what? Random states. So it can be 52, 42, 59, basically any value you can think of. Okay, but the point is, you use these values, you keep tweaking these values until you get a model that behaves or is okay for you. All right, and that's what to use. So you get the best model for yourself. Now I have 4 variable names here. Okay, X train, X test, Y train, Y test. The reason I have this 4 is because I'm expecting this thing to split my 2 groups into another 2 groups. Okay, so if I have X and I have Y and I want to split X into 2, right? I'm going to get what 2X or 2 groups for X, right? And then another, basically means the terminology test X and what train X, right? I'm going to get the 2 groups. Then if I do the same thing for Y, I'm still going to get test Y and what train Y. Okay, thereby giving me what 4 values now. Okay, or 4 groups basically. Okay? So that's the idea. So the next thing I was doing was to do what? Check the size of this particular what data. Alright? I know that I chose to split it by 30% or yes, 30%. So I want to know how many data is still remaining from our what 164 data. 30% of it will be giving me somewhere like 50, which is what I'm seeing here. Okay, then the 70% is what 114 thereabouts. Okay, so that's the splitting ratio. So the 114 is for what training, while the 50 is for what testing. Okay, so that's the idea we are going with, and that's how we do it nearly every time. Okay, this basically, this part is something that you don't get over with. Okay, something that you just have to know it. I can switch this instead of using test size. I can use train size. If I put train size there, it means that I'm giving a training size, which should be what 0.7. Again, I can choose to go with 50-50 if I have very large amount of data. Okay, if I have like 12,000 data, right? I can choose to go with 50-50, which is still okay. Or I can choose to go with 60-40. Alright, 60-40 is still okay. But in most cases, 70-30 is where you find yourself for small data. Okay? So that is that. So the next thing we do after splitting is to start our model selection and define our model. Now we are doing linear regression. Okay, in reality, you may not just pick one model. Okay, in your real job, you will not pick one model. You might start with linear regression. After you've done training for linear regression, you use another model. Your aim is to find the model with the best performance. Okay, your aim is to find a model with the best performance. That is your aim. Now there are ways to train multiple models as they go. Okay, way much more stuff you can look into that and learn more of that. But ultimately, for the sake of this class, we'll just do one model. The process is still the same thing for most models. Okay, most models have the same way. In our case, we are choosing a linear regression model. Now, the simple thing we do is to define a variable called model, which can be any name. Okay, it can be any name equal to what? Our model. Okay, the linear model. Okay. Now we have, remember our classes in Python. Classes have methods. You should remember, right? And when we call a class, we normally call a class by putting parentheses. You should remember, right? So this is a Python class. Think of it like that. Okay? Now in this Python class, we've created it, and then we are now calling the .fit method, and it's inside of it. Okay? So we are now saying model dot fit, which is what? A method inside of what? The linear regression class. Okay, we should remember all those parts. So now the dot fit method is what we use to train our model basically. The dot fit method is what we use to train our model. Here we are passing in our training data, the X train, okay, and the what? Y train. Okay, so we are passing these two here for training purposes. Okay, for training purposes. A lot of things we have skipped along the way, but for just a simple data set, there is no challenge. Okay, there are some things else I would have wanted us to see, but you will see it in the next class. Okay, I think I have one more model I was going to look at under supervised machine learning. I should. Sorry? No, just copy from this one. Okay, you've not reached to this point. Don't worry, once I'm done, I can go back for you. Okay? So, now after we are done training may take 5 minutes, 2 minutes, 3 minutes, depending on your system and depending on your data. Okay? If I have 12,000 records or a million records, it won't train as fast as someone who has 20 records or 500 records. So the number of records you have or the number of data you have, okay, also affects your what? Training speed. Okay? And your system as well affects your training speed. So most times, most of this high level training are done using what? GPU systems. Okay? So that is that. Just bear that in mind. Now for my own model, I am checking for the model accuracy score after training. Now this accuracy score here is not accuracy on unseen data, but accuracy of the model that just data that we use for training our model. Okay, we're trying to see how accurate did this model learn from the data. And from what I'm seeing here, I'm seeing 0.98912 on the rest of the numbers. So judging by this, I can say we have 0.89 accuracy level or 0.9, which is like 90%. Okay, so that is that. So the model was trained at what? 90% accuracy. Then the next thing we are going to see after this level is to see how the model performs against unseen data. Okay? How the model performs against unseen. So if you have seen dot fit, you have seen dot score. Okay? We have dot predict We have other ones, but these are the major ones we need to know about. Dot fit, dot score, and dot predict. Okay? So this is like the round up, basically the same thing. Now for our prediction, this is what it looks like. Okay, model dot predict. Now in prediction, I'm only passing in what? The x value. Remember the goal is to predict something. Okay, to predict our y given our x. So we want to know what y is given that we have what? X. Okay? So we have x, we don't have y. But we have trained a model that knows the relation between x and y. So when we give it x, it should tell us what the y should be as accurate as possible. Okay? So which is what we've done. And we have seen that our model has the ability to give us what? 89% what? Accuracy. Okay? 89% accuracy. Which in most cases we call it what? A good model. If you have a model that performs close to 80%, that is a nice, very, very nice model. Okay?
It's 9.3 is not a score. Percent.
Yeah, it's a percent. 0.893%. We convert it to percent, becomes 100. The score you're talking about is basically for between 1 and 0. So anything between 1 and 0 is virtually done a percentage. You're considering it, if it's closer to 1, be better for you in this case. If I'm using score, if it's closer to 1, better for us. So 0.9 something is already a very perfect model. Okay? So 0.8 something is a great model. Okay? So that is the idea. Having a 1 rarely exists. Okay? But should we have 1? That would be great.
That's to say one is a perfect one.
1 is the perfect model for the most time. That means it learned everything great. Okay. Now, the score we are getting here is basically telling us how well the model is doing, not how accurate our answer is. Okay? How well the model is doing, but not how accurate the answer is. The model can be doing very, very well and be giving you wrong answers. So it's possible. Which brings us to another method we use for what? Checking the loss or the difference between the actual value and the what? Predicted value. Okay? So this part, you want this part to be close to 0 as possible. Whereas this part, the score part, you want it to be close to 1 as possible. Again, the score part, you want it as close to 1 as possible. Okay? Whereas this other part, the part we're choosing our mean square error to check the difference between the predicted value and the actual value, you want them as close to 0 as possible. Okay? If you're having high values, that means there's a big gap between your predicted value and your actual value, which means like an error, a large error gap. Okay? For instance, if it predicts that the house price should be 2,000 and the actual price is 1,800, you are seeing that you have 200 gap, okay, which is a large gap, right? But this model can still be what? 90% accurate. Okay, so that is the idea. So just know that the accuracy does not equate that it will give you the actual score. Okay, it may not. It may give you a value close to it, as close as possible as it can get. Okay, so that is that. Now we're looking at the mean square error, which I wrapped inside the NumPy square roots method. Okay, so this of what is a function. Yes, function. Okay, so basically what I'm doing here, I'm using the mean square error to find the difference between what the predicted value and the actual value. Okay? Once I get the difference, I find the square root, and it should be close to 0 as much as we can. So we have 78. Okay? 78 is good. Alright? But if we train another model and that model is giving us 68, that model is better than this one. Okay? So the idea is to get close to 0 as possible. If I can have 0.0001, that would be perfect. Okay? But in most cases, it's always not possible. Okay? So the closest you can get to 0 is your best model. That is why at times you have to try different combinations to see which combination gives you the closest to what? 0. Okay? So that is that. So, now, if we are done with what? Our model training, model prediction, we are even gotten to the point where we can check how accurate our model is. We've seen how to check how well the model learned. Now we are seeing how to check how well the prediction is. Do you predict it accurately or not accurately? Okay. So seeing that we have an average of what? 78.86 marginal score difference, okay, or gap between the actual value and the real value or the predicted value. That means if the value is supposed to be 100, okay, it added 78 to it, or it minus 78 from it. That is what this part is telling us. Okay, it added 78 to it, or it minus what? 78 from it. So that is how far we are from the actual value. Oh, that is what to note. Okay, when you start working in big companies, just know that this predicted value might not always happen. Okay, so we may come close to it, or we can go above it. But being at the exact value may not always happen. Alright? So that's basically a simple linear regression. Again, like I said, we jump some processes, okay, because of the kind of data you are working with, just basic introduction class. Okay? But again, we'll learn and see all those ones. And if I'm to plot this thing, alright, this is just basically showing us how well our model is fitting. Like I said, based on our target variable, which is the calories, okay, against all the other details, okay, you see that the best one that had the best line was the what? Duration. And I could tell from the beginning that duration had what? The best correlation as well. So all these other ones couldn't fit properly. Okay? All these other ones couldn't fit properly. So the meaning of this is, if I remove these ones to train this model, okay, I will have something better if I'm only using duration to predict the calories based on the visual I'm seeing here. Okay, this visual, like I said, is just showing us how each of the data points in our X values, okay, contributed to the what? To the model's performance. That is what this is showing us. How each of these points contributed to the model's performance. Okay, so if I look at this and I see, okay, the only model that, or the only feature that actually aided my prediction was this one that tried to find a perfect fitting line between the data points. Okay, the other ones couldn't actually make meaning of a linear model. The linear models are almost always like this or like this. Okay, but having a linear model going this way doesn't look good. Okay, so we couldn't actually find any linear regression or linear relation rather between this and the calories, right? So that is that. And again, without even plotting this graph, I told us from the beginning when we did correlation that this and this were highly correlated. Therefore, if I'm to just choose a single feature, I'll just go with what? Duration. And then forget the rest, okay? and then plot my stuff and go my way. So I would allow us to copy, for those of us that are here. I think that's the last part. Okay, now the actual and the predicted values. So this is the predicted value, this is the actual value. So looking at this, you feel like they are close. At least for this one, it's almost same thing. Okay, but this other one is quite distant. The rest for this. So in some places, it was able to come too close. In some places, it went too far. Okay, so that is one thing to note, right? In some places, it came too close. In some places, it went too far. Like 150 and 185 or 184. Okay, that's too far. All right, 600, 468. Okay, so those kind of values. So, but this is basically what we have: the actual value this way, our predicted value this way. Okay, so now I think this was a random something that we did to test and to do all this. Okay, but let's, for those of you that have not copied, you can start from here and continue what you're writing before. Okay.